Okay, thank you very much, Louise. It's like said, I have worked in many applications. I will talk about only one of them. It's the applications are not so important. It may sound strange. What is important is that you keep your discipline. So I'm a plasma physicist, so I work in many applications. Applications pay the bill, but in the end it's all about advancing plasma physics. That's our job as university researchers. I have chosen one topic to talk about. I will not dive deep into plasma physics. I understood that the audience is very broad, so there are people from all kinds of departments. So maybe I have to disappoint Vasco that I'm not going to dive very deep in plasma physics. The application I will talk about is semiconductor processing technology. And I've chosen this topic because there the field is changing again. It has changed a lot 40 years ago, then it was stable for a number of decades, and now it is changing again very rapidly. So this is where I will focus on. Let me get the pointer. So that's the title is CHIPS Act and Diversity. CHIPS Act, those are issues that I will be starting about. This is all about semiconductor industry, the role of plasma physics in there, and the needs of the industry and how we can live up to those needs being a university, because one thing we all share is that we work in a university. But in a university we also need diversity. If I look at this audience, the percentage of female people in the audience is about maybe 15%. This is really not good. I don't want to disappoint all men, but we are not doing a good job there. But I will show you that you can do this better. So first, the CHIPS Act. So it took a long time. I will briefly first give one slide with a little bit of history. CHIPS Acts do have a history, they do have a present. Whether they have a future, that we will have to see. I will highlight a few of the present day challenges for plasma physics in semiconductor research, semiconductor technology. Because that has changed as well over the last decades. And then maybe also point out the strong points we can offer to the world as being Europe and having the European ecosystem in terms of science. And after that I will change to diversity. I will highlight a few issues, and at the end there will be something like an exam for you. You will all be handed out a page of one A4 page of a job description, and I will first tell you how it should be done, and then you should indicate on that sheet what is wrong about it. And this is a job description which is coming from a normal European university, just found on the internet. So this is just to illustrate that it is so easy to do things wrong in this respect. So now the CHIPS Act, they are now in place in Europe and in the US. There is a history. About 40 years ago, there were two major initiatives. In the United States, this was Sematech, as it was called. In Europe, we had JESSI. I'm pretty sure that part of this institute was involved in JESSI. There is no escape. Almost all of Europe was active in JESSI. There are a few major differences between the two. First of all, they started at the same time, roughly. The big thing is that in the United States, the consortium was led by government. It was at that time the Department of Defense which was doing it. In Europe, the consortium was led by industry. The aims were the same. So 40 years ago, the Japanese were the prime suppliers of technology. The Japanese industry was catering to the world. So this needed to be changed, so that's why we had this initiative. Sematech was there to re-establish American lead in semiconductor technology, and Europe followed and tried to do a similar thing with JESSI. Sematech had a central location. It was in Austin. JESSI did not have a central location. The funding by the government of Sematech was huge, $500 billion. In Europe, JESSI was 1% of that, 5 billion. So imagine this difference, and then it's not easy to think why Sematech became a success and JESSI became a failure. It's not all about money. It's never all about money. So it's more than that. But money does play a role. If you have 500 billion to spend, even and the size of the continent, the size of the US is roughly the same size as the size of all of Europe. So then that is already a reason why the European initiative failed. Another reason why it failed is that it was led by industry. Philips at that time was still a very strong semiconductor company, and they withdrew in the 90s, and with that they decapitated the JESSI program. So then it slowly died. So it started as being 1% of the US, and it ended up being totally irrelevant. So now the difference is that this was hugely successful. The Sematech, the result of Sematech, you can see if you drive from San Francisco to San Jose. You go along this US 101, which is the backbone of Silicon Valley, and you have Intel on your right, on your left-hand side, and Apple on your right-hand side, and all those big companies are on a 1-hour drive. This is, I think this can be more or less straight be attributed to Sematech and what this did to the industry. So now a similar thing happened. So this made sure that the US gained control of all the processor technologies. All the processors are built mostly in Intel, so in the United States. But now the major counterforce is China and Taiwan. It's no longer Japan. So now we have to fight Chinese and Taiwanese supremacy, and the US is doing this by, again, boasting out a lot of money, 280 billion, all government money. This is released in tranches, so 50 billion have already been released, 80 billion is coming, and this is again done by government, but now it is spread over a number of departments. So where Sematech was the Department of Defense, through DARPA, this is now Department of Energy, Department of Defense, and all kinds of departments, Department of Commerce. They all work together. So this is like they do this in the US, big money, made available at once, not that many conditions up front with a clear target. Europe again is trying to mimic this on a much smaller scale. So Europe now also has a CHIPS Act. Now even the name is the same. It's called CHIPS Act. Well, not officially. I think in the US it's called CHIPS and Science Act, and in Europe it's called the European CHIPS Act. So even the name is the same. In Europe it's 40 billion, so a factor 5 less. The aim of the United States is strengthening the American supply chain and countering China. So not even that much Taiwan, but mostly China. In Europe, the aim is to increase the market share of EU in chips production from 10% to 20%, which is a totally different goal. So the European goal is not about technical excellence. It's about volume. And the United States initiative is about excellence and technology. So the approach is completely different. I will not make any predictions about the success. We have to wait 10 years, but if you look at the messages that speak from how these things are shaped, I personally am not investing a lot of time in the European CHIPS Act. But this is my choice. Feel free to do it if you think it is appropriate. There is another difference. In the United States, our plasma colleagues have united. This was done under the leadership of Mark Kushner. Mark Kushner mobilized all of the plasma teams in the United States, and they lobbied with the people who were writing the framework for the CHIPS Act. And they made sure the word plasma is in the CHIPS Act. So in the United States CHIPS Act, there is one sentence. It's on the internet, and this says that part of the technological directions to foster is fundamental research in plasmas and matter at very high temperatures, and it is also the development of fusion energy systems. So for IST and the physics department, this would be a golden opportunity. It's fusion, low temperature plasma physics, and this is all fostered. But this money is spent in the US. At the last JESSI, where a few of you were present, there was a workshop on this, and I offline asked people of this initiative whether Europe could participate in the United States actions. The answer was no. So maybe we can sneak us in, but I don't think that this is possible. So what we see here is that the United States takes a bold step, Europe takes a smaller step. United States scientists unite and enter those initiatives. European scientists, all of us, including me, we don't do this. So there is a job ahead. I will come to that a little bit later. The rest we have work to do. What the US also did, in parallel to this, they created plasma facilities. So there is not a lot of money available for that, 6 million per year from the Department of Energy, but they did make statements that a lot of the research is actually coordinated from a few locations, and for low temperature plasma physics, this is the field that I work in and that many of you also work in. This is concentrated in 2 locations, in Princeton and in Sandia National Laboratories, where the modeling part is almost fully concentrated in Sandia laboratories, and the experimental part mostly in Princeton. So there again, the United States have chosen to locate the efforts and to focus the money on certain areas. And this is typical of the American ecosystem. In Europe, we have no focus and we don't unite yet. But so here we have something we can do in the future. We have to exploit our strong points. So what are the present challenges related to plasmas? There are many challenges like photoresist and logistics, and so I will not address all of those. That would take forever. I will address what we as plasma physicists can do. In the past, the main question was process quality. So 40 years ago, the question of industry was increase our etch rate, increase our deposition rate, increase uniformity, make sure that we can etch below 1 micron, make sure that we can do this on 2-inch wafers, which was at that time the standard. So the 2-inch wafers is about this size. Later on it was increased to 4-inch, about this size for a silicon wafer. So those were the questions in general for Sematech and for JESSI. Nowadays, basically those questions have been answered. The technology is there. We know how to make the processes as selective as needed. We know how to go to submicron. We even know how to go to nanometer size. So most of the questions of 40 years ago have been addressed. And this was an interplay of academia and industry. So industry could not have done this without academic research. What is happening now? We are moving to different regimes. Aspect ratio, if I go, this is a picture, just a picture, one picture of something that we have to make now. If you look at these structures, this is not even a real device. So in the past we were used to having a trench which would be 2 or 2 times as deep as the size of the hole in the pattern. Nowadays the trenches go down, well, 10 times or hundreds of times the size of the pattern. So that means that the demands on directionality of the etch process and of the chemical selectivity, those are exploding dramatically. So what it means is that this you also have to do on 30 centimeter wafers. So this is the wafer size, not this, but this. So you have to make those structures which have a top angle. Imagine that the angle which is required now in etching structures is 89.96 degrees, I think. So this is extreme directionality. So we have also, as plasma physicists, we have to go out of our way to control ion velocities and the direction of that and the variation and the angle. So the challenges are back, but then more extreme. And you have to do this over this wafer, not this. So if you have this directionality in the middle, it should also be there at the edge. So the demands have become more extreme. Sizes have reduced. 40 years ago it was 1 micron roughly. Nowadays these are pictures of real devices. You see one device here, an NMOS, PMOS, this is 13 nanometers in size. So we are approaching atomic limits. So if you know that 13 nanometers, that is roughly 30, 40 atoms on a row. So we are closely approaching the atomic limits of what you can do in matter. We are approaching the regime where matter is no longer matter, where matter is just a bunch of separate atoms that have to be processed. So sizes are approaching nanometers and are so what is called the node size. At the moment the node size is 7 nanometers. It's supposed to go down by another factor of 2 in the next 5 years or so. And then we will be at the atomic limits, so then it will probably stop. But the last factor of 2 we still have to do, so this is, in a nutshell, is what we have to do. Aspect ratios of less than 1 millirad, so that's the angle, across a wafer, and this has to be done lot to lot, wafer to wafer, factory to factory. All very reproducible, and sizes are nanometers. So what can we do as a plasma physicist? From the wording already you can deduce that we have to go to atomic sizes, atomic precision. The engineering and productivity has to be increased enormously. We have to, so now a kiloparticle is no longer 1 micron, a kiloparticle is 2 nanometers. And so these are the small nanometer sized particles that pharmaceutists use in medicine. They penetrate the skin easily, so that's the size of particles we are talking about. And then of course the usual things like process diagnostics, simulation of processing, and we are moving towards digital twins of complete processing machines. So I think at this time the future for modelers is actually a lot brighter than for experimentalists in this field. There are a few moments, but this is one of the moments where I actually am pity that I am an experimentalist. It's better to be a modeler now. But the main question of industry now is not so much the technology. Of course, they need new technology. But the main question of industry 40 years ago was give us the new technology. The main question of industry now is give us people, train skilled plasma physicists, train skilled device physicists. So that's where we can actually do what is needed by society. And this is what we do as a university. We educate people. But we don't align this necessarily with the needs of our customers. And this is where we can make some steps, I think. So a few examples. So I had to sneak in a little bit of physics and chemistry in this talk. Oops. this is something that I was not supposed to do.
I imagine so. Check if the connection is still on.
I will stay away from this corner.
I think it's okay, right? Okay. You can.
I'm back online. Back online again. I will try to avoid that corner. Yeah, I have my remote, so that's why I was given the remote. So for going to atomic level, a logical step is to do this by atomic level processes, so like atomic layer etching, atomic layer deposition. What you see now happening in the industry is that there is a massive transition from classic plasma etching systems to atomic layer etching. This is something that still needs maybe 10 years to complete, but this is a definite movement in the industry. So it is wise to connect to these topics of research for technology. Another aspect is that the wavelength of the light, if you go to 6 nanometers, has to go down. So at the moment EUV technology is the only way to mass produce chips of these feature sizes. My own luck being in Eindhoven is that this whole technology has only one supplier, which is called ASML. And they are on our doorstep, so the ASML main research facility is 20 minutes on bicycle from my laboratory. There is a lot of collaboration going on. But what you see now is that in the United States people are slowly getting more and more interest in EUV. So everywhere in the world people will start entering EUV technology, and so including sources to produce EUV. So one of the challenges for plasma physics is sources of EUV. The present approach is actually just power play. These are 10 droplets. They are size of a micron roughly. They are dropping into the focus of a laser beam. This is a mirror. So the orange part is the laser beam of a CO2 laser, which heats the 10 droplet, evaporates it and creates it into a plasma of 40 electron volts roughly. And that then emits the required wavelength of 13 nanometer. This is known technology. It's all very extreme. These droplets fall by in a frequency of kilohertz. So every fraction of a millisecond you have to fire a plasma and extinguish it. And then the photons will be transported, but what also happens is that all these EUV photons, they have an energy, photon energy of about 100 electron volts. So they can ionize, and they will ionize. There is hydrogen in that reactor for all kinds of purposes. So the hydrogen gas is turned into a hydrogen plasma by the photon flux. So much that the ionization degree is tens of percent, so it's actually ionizing quite a large fraction of the gas. It means that all of this volume, and this goes for all of the purple action, this is the EUV beam which is produced here, goes to about 10 mirrors. Here is the reticle, so that's where the slide is which has to be imaged. And here is the wafer. And these are all just magnifying mirrors. All of this purple volume is a plasma. It's a low pressure EUV induced plasma, but it is a plasma. It accelerates ions, it does damage to surfaces. And this is a new area of plasma physics where we have entered with our group 10 years ago. And I like the area because it's extremely non-equilibrium. It's if you fire an EUV pulse, all of the stuff is ionized, all the electrons fly out immediately. You have runaway on a large scale. So it's extremistic plasma physics, which I like. But this is an opportunity for research. This is not ready yet. It works the machines are sold, but the industry still needs to go up by a factor of 2 or 4 in terms of throughput. Yeah, it still works. To give you an idea of how big these machines are, this is then the EUV beam. The total machine which does the illumination, oops. The total machine of which does the illumination, these machines are the size of a train wagon. So it's the length is between the walls of this chamber and from the back wall to here. That's the size of one machine. The price is about 200 million, 2 or 3, 400 million, depending on the options. Like when you buy a car, you also can buy electric windows. When you buy a machine like this, you can have all kinds of options. So this is extreme plasma physics. So the attention for our fields for plasma physics is moving towards surface-related aspects. The bulk plasma is more or less understood. We don't understand yet what is happening at the surface. That's where a lot of work still needs to be done. So this also goes for the gas phase. In terms of diagnostics of the gas phase, we have to move to microns precision, very close to the surface of the wafer or the reticle. Modeling, again, the modeling of this type of plasmas, of EUV-induced plasma, and also the plasmas used for ALD, is not very well developed. It requires a lot of chemistry modeling. It requires much larger gradients than we are used to. So in modeling there are many challenges to tackle, and these are all related to what is happening close to or at the surface. I'm just giving a few examples. This is one example of our own lab. One of the parameters that is now getting very important is what happens to the electrical fields which is accompanying the plasma. Plasma always has electrical fields around it, so even EUV plasmas have this. When those plasmas hit the surface, the charge at the surface is actually flowing, and these are examples of measurements. This is not simulation of the electrical fields in the surface measured with Pockels effects while a plasma pulse is extinguishing. So it hits the surface and then the fields spread. You have to go to surface proximity diagnostics. So mass spectrometry is an option. Optical diagnostics could be an option. You have to go to surface diagnostics. So everything has to go to extreme regions, very small dimensions, very high resolution. Maybe we even have to adopt techniques which are not common in plasma physics. Like for instance, confocal microscopy is very common in medical sciences. The medical scientists use this technique all the time to look at cells. We might have to move to those techniques to diagnose our plasmas close to the surface. So we have to import techniques from other fields. The modeling, you probably know this person. There is at the moment, as far as I know, but you are much better aware of this, there is one code which is used by several groups in the world which can actually do molecular dynamics modeling of a surface, of solid state surface which is interacting with the plasma. So this is all based on molecular dynamics. I think it is ab initio molecular dynamics. The inventor, well, the person who created that code is Barbara Gerritsen. Oops. There is some artificial intelligence in this thing. Barbara Gerritsen created that code, and this is now used in various locations. I'm not sure if you are using it here. But this may be an option to use. It's available and it works quite well. I think that David Graves has also used this code in the past, and also people at Philips. Annemie Bogaerts is now using that code, so it is still there. This is one of the few options of measuring interaction between the plasma and the surface, and for modeling very close to the surface, it's not enough to just model close to the surface. You have to model what is happening in those deep trenches. So you have a hole which is well, half a micron deep and 5 nanometers diameter or so, and you have to model your transport in that hole using Knudsen transport and all the tricks of the trade. So also for modeling in those structures, we have to enter for us uncommon regimes. Mark Kushner is already doing this. Well, Mark Kushner has a habit of entering new fields regularly as the first in the world, and he has done this again as a first, I think. So, how light is it? Oh, I have to speed up a little bit even. For this you need a trained workforce. So I said just continue with the diversity. The workforce you need is trained in plasma physics but also in general technology. But it also has to be diverse, and this makes the bridge to the next topic. If you want to increase diversity in the organization, you need this for changing decision-making processes. It's not just for numbers. It's not important to have so many women or so many gay people. This is not the target. The target is to have an organization which is balanced, where decisions are taken in a balanced way. That means that also diversity is an issue. Well, maybe this is something before we go to diversity. One thing I would like to do, and therefore I would like to do this together also with IST. I mentioned earlier the industry is crying for people. They're crying for trained experts. We can do this. We can make courses for people in industry and train them to do plasma physics or to do surface chemistry or whatever is needed in the branch that they are working on. My idea is to do this in a worldwide training program which does not exist yet, so we have to create it. I think it is hopeless to get to get government funding for this, so my idea is to get company funding for this. I already have companies like ASML and Lam Research. They have already expressed they want to support this. So it's basically just up to us to do it. So I will approach the people here, the colleagues in plasma physics, separately. My idea is to set up a network of 10 universities worldwide, 5 in the US, 5 in Europe, make a training program, have 4 editions of on-site training per year, so that people don't have to wait a full year. It should not be the same as the Bad Honnef summer school. It's not about science, it's about technological know-how in plasma physics. So it's a different approach, and then we just make industry pay for it, so we are independent of government things. Governments are very unpredictable, typically. Industry is much more predictable. Well, I'll just skip this and move to diversity, otherwise what I'm going to tell here is not something I invited and I invented myself. I got inspiration from the University of Ann Arbor and of the University of Groningen. I went there, so I took a special trip to Ann Arbor, not to see Mark Kushner, but to see the diversity team in Ann Arbor. So I spent a whole day speaking with people of their diversity program. They have an advanced program which is headed by, I think, 2 or 3 full professors who do nothing else but diversity issues. So they don't have to do any other thing in the university. And they have a whole large staff of support people to help with recruiting, with the scouting. So all the steps that are relevant. So after getting all this input, we designed our own program in physics. The result is that, well, the award is not so important. We did get the diversity award of the Dutch Physical Society. What is more important is that in our department, the number of female PIs, so we have a department of 60 PIs, 60 full associate and assistant professors. 10 years ago, we had 2 women, now we have 35% women all over. So it does work, but it requires 10 years. So don't think you can do this quickly. The main, maybe if you want to remember something of this lecture and you want to learn about diversity improvement, this is the thing to remember. This is by far the most important notion to promote. I have to stay away from this. So this is by far the most important aspect. So the main issue is not only having good procedures for selection. The main issue is get the female people to apply. There is a famous, a joke almost. Take a list of 5 requirements for a job. A female candidate will fulfill 4 requirements of those 5 and will not apply because there is one which is not fulfilled. A male candidate fulfills 2 or 3 and says, well, I will apply. So many more male persons, many more than the fraction in the population will apply. So the main job is to take away this list of requirements. So don't have this list of requirements, but make sure that the people who you think could apply actually feel invited to apply. So that means several things. One thing is the text of the vacancy. I will give you examples for this. This is crucial in attracting a diverse workforce. The text of the vacancy that we normally use as university is totally discouraging for a diverse population. I will demonstrate this with the little exam at the end. And then, this is maybe even more important, approach the candidates. So when we started with this, I was dean of the department. I asked, we had 6 vacancies. We decided we only wanted to hire female female candidates for those 6 vacancies. And those vacancies were spread throughout the department, so from the quantum groups to plasma groups to fluid dynamics. What I did is asked the whole department to supply lists, names of potential female candidates, and also a list of names of people who are in charge of laboratories who might know female candidates. I personally sent out emails to all of those 250 female candidates, person by person. It took a Sunday afternoon, but that's worth it. And I also followed up on all those emails, so you get responses and asking questions. I did this while being the dean. I discovered later that this was the essential condition. This should not be done by a recruiter, this should not be done by an HR person. This should be done by somebody who is actually believed. Because the main message of that email was, you qualify, please apply. So it was formulated, it didn't say that, it was phrased in another way. So it says something like, we have a position with this profile, your name was recommended by this and this person in our department, we believe you would fit this profile, please consider to apply. Something like that was in the message. So I sent out 250 emails like that. We got, well, in the end it was like about 100 applications, 70 were serious. And we did hire the 6 female, we had 25 interviews and we did hire 6 female candidates. I asked all the 25 people who came for interviews, I asked whether they would have applied if they would not have gotten my original email, and the answer was no, without exception. So that is the first and most important step. So when you want to increase the diversity in the department, use a personal approach and have it done by somebody who is believed. So it should be a leader of the field, it could be a department head, but somebody with credibility that people actually trust, and then that same person has to follow up. So it takes time, yes. It takes lots of time, but it is worth it. So this is all in these lines. So approach the candidates and lower the boundary so that you also get the passive candidates who not automatically apply on every occurring vacancy. You even get those to apply. And then, of course, you have to do everything else in the procedure correct as well. So make sure the interview team is diverse. Make sure that the total of the interview, so you invite the people or you make them visit people in the department. Make sure that the people you invite feel at home, they feel welcomed, they feel appreciated, they are accommodated well, so make sure hotels are arranged, that all reimbursement stuff is done easily so they don't have to walk several miles to get their money back. So facilitate the whole process, and these things may sound not so important, but it's in the details. It's the details which make that a approach works or not. So the interview team should be diverse. So that means that you have to make sure that an appropriate number of female colleagues are in that selection jury. I had a case where there was one interview and one of the candidates actually did not perform well during the interview and the discussion, and all of the male members of the jury said, well, dismiss this candidate. There was one female member of the jury who said she probably misinterpreted the instructions and misjudged the situation. So then I, being the dean, I dismissed all my male colleagues. Well, I didn't dismiss them, but I just invited the person, that candidate, back for a second interview, and then she passed with all colors. So you need, in the jury, you need to make sure that the signals that are sent, which are not picked up by male colleagues, are picked up. So there is many places where you can go wrong, but in most cases this aspect is going wrong. So you just don't get the candidates that you want to apply, that they apply. So you have to make sure that you make that step properly. Then once they are there is a onboarding scheme, so you select a candidate, a female candidate. This is true for female and male, but even more for female, one aspect at least. So ensuring a warm welcome and finding their way. This is all similar for male and females. What is also similar in the effect, but what is different in the need is support partner employment. Female scientists often have a partner who is also a scientist, who is also active, who has a job in the technical area. And so you have to accommodate that. For male scientists, this is not so often. Then there is a much larger variety in the profession of the partner. So especially with male candidates, with female candidates, it is very important to facilitate partner employment. And I'm not meaning that the university should hire that partner. This is not possible, but you can, like we have in Eindhoven, a service which is a commercial company. It's called Eindhoven Expert Service Initiative. So they do one thing, it's a company, and the only thing they do is finding jobs for partners of people who settle in the Eindhoven region. Not just for us, but also for ASML and for other employers. And of course it's also important to find a mentor, a coach or a guiding angel for everybody who starts in the organization, but especially for female issues. But I didn't write that down, but in our physics department we have a special female full professor who is also a confidentiality person for all female staff for issues they don't want to discuss with a man. And that is working. That person is approached 4 or 5 times a year and can take initiative, can go to the board to repair things that go wrong. And of course nobody wants to bring out any open that something is wrong, but in this way you can facilitate so you can repair damage, even when the people have already started. And this is in one case in my department. This actually happened. One of the starting female assistant professors sort of cried out to this confidentiality person that she did not get enough technical support, so that confidentiality person came to me, addressed the issue, and I could then arrange that there was adequate technical support. So you can, it's not just signal, it's also following up. So you have to be prepared to accommodate things that go wrong. And the whole process, emotional intelligence, is the key. It's not about citation and the chess, and these are relevant for selecting, but for diversity, this is not the most important thing. Another thing which has to change is the culture of the institute. Good, welcome. What we did, and this is, we followed up on the Groningen initiative here. We learned it from that. All committees in the university, all boards that advise or take decisions on either money or people, need a diverse composition. So this is true for departmental councils, for all important committees. This puts a strain on the female colleagues because there are fewer still, but as the numbers grow, like in our institute now, we have 35% female, so then the strain is not that much more. So what you have to do is make sure that the composition is at least as diverse as the population, but make sure that all sides are heard. This is not for the numbers, this is because of the culture. Female professionals listen differently, sense different things than male colleagues. And that is important for taking decisions, because then being a man, you don't understand, you just don't sense, you don't get that something is not right. So for that you need the input of female colleagues. Also all people who are personally as an executive dealing with money or people, so all department heads, all directors, all people in executive levels have to go to inclusive leadership training and active bystander training. And those are really confronting courses where people have to learn it in the hard way. I went through those courses as well. And I can assure you it's very, especially the active bystander training in our university was, I didn't sleep that evening. This is really confronting. And then also, as the organization develops, also the executive levels will be filled with female colleagues. And that means that you have to get the organization ready to accept this, because present day universities, the culture is just not, people are just not used to having women at the top. And in my own university, the present rector is a woman. The previous 12 rectors were all men. So what I hope is that this now actually changes the culture also. I don't blame you for being a man, but I think it is. I think it is. Well, I think it is important that the organization is made ready to accept this change of culture, so that the organization is actually changing. So I already highlighted a few things, like what we did. Why is it going back? Yeah, this, the culture, the acceptance of diversity is something that people need to get aware of. This is something I discussed earlier with your own. Awareness is key, so people have to be aware that it is not appropriate, not normal to have a male-dominated institute. that it would be much more normal than to have a balanced institution. And that also decision-making processes are then done better. And this is something that is not standard in the culture. And the dual career issues, they need to be supported also in executive layers. I can also give an example here. We were hiring a certain person. The partner of that person was a professional, was an associate professor in classic languages, in Greek and Latin. We are at an engineering school like IST, so we don't have classical languages. So I, being the dean of the department, I went to the director of my university, approached the director of Nijmegen, where they do have a classical language, and there we were able to explore the option for landing the partner. So sometimes you have to go on a national level, so the size of Portugal is not that different from the Netherlands, so it's overseeable. You know all the directors of all the other universities. So even on that level you have to be able to help each other as institutes to accommodate partner issues. So how we did it in physics, don't try to read this. This is the text of the advertisement. I will focus on parts of it. No, not yet. This is the text of our advertisement when we started to advertise for the 6 positions. So on the left is what, on the left is what I had made up just as a standard text for the advertisement. I sent this text to the 7 female colleagues we had at that time and asked them for input. The rest, and the text in the end was completely different. I didn't recognize my own text anymore. And I will show you a few items where it was changed. This was a standard phrase of the university which was put on the top of all advertisements, university-wide. So it just has the usual thing. As a university we educate, we train, we do research, and we do this all at top level. So the usual blah blah that all universities have on the top of all of their recruitment text. And what came out is that we started this text with a statement that diversity broadens our research scopes and enhances the quality. So we made a complete turnaround of the intention of the text by reformulating it in this way. This continued for for the rest of the document. Why is it not advancing? Now it is. So then it described, the standard text describes that we have 12 research groups. This was all done interactively so that everybody could just click there and be directed immediately. But also it immediately stressed the fact that all the PIs are independent. So there also was a link to all the PIs, which was totally lacking here. So this is just another stress point that you choose in the text. This was the standard ending, open only to female candidates. And this was what came out after the review of my female candidates, of my female colleagues. So you see that the text changes completely. This was an eye-opener for me. I had not expected this. I thought, well, I've done this before, I'll just write a recruitment text. And then I found out that my text was totally useless in the framework of trying to acquire a more diverse population. Another thing is that I didn't have a slide for that, but I can illustrate it here. What it says here is that there were short descriptions, and also here, of the positions. Normally, the profile of a position normally is about 1 page. It describes the context of the position, it's in this section of physics, so it's condensed matter. what I did is I forced my colleagues to formulate the profile in a maximum of 3 words. So these are all, this is a profile, permeable media. So all those profiles were formulated very broadly so that a large category of people would fit. So this is one of the recipes. Don't make profiles too narrow, because if it is a narrow field, the total number of people who could apply for that is small, and looking at the present distribution of male and female researchers, you will automatically have better chances for the male. So make the profiles very broad as you can possibly can. Then the procedure, I already highlighted this, so I sent out these 250 personalized emails. I followed up on all of those emails, and in the email I also suggested the option that people who could have a conversation with me and the recruiter just to get questions asked. So I had about 50 or 60 informal talks with candidates who did not apply yet, but who just had questions. And then after that they all applied. And then we also had a test lecture for all candidates, but this is now standard in our department. We are in the physics department, so everybody who applies for a job in our department gives a test lecture on Snell's law in 10 minutes. The same for everybody. But this is not particular to diversity issues. The result, these were the colleagues we had in 2012. This is the colleagues we had in 2022. We actually have one who came from here. And now it is still continuing. So now we are at this level of 35%, and people do still come in. We are not done yet, so we have to maintain, even also my successor as dean, is maintaining this approach of increasing the diversity in the department. It requires a consistent approach of roughly 10 years to change it, really. So all those 10 years it has to be consistent, even though leadership changes. So this is the difficult part. The takeaways I already outlined. The first step is the most important one. Have an authority send out the first email and make sure that that first email takes away the first doubt. So that email should tell the people, you qualify, do apply. And then do everything else appropriate as well, but the essence is in the first step. What is also what I found very convenient and also correct. I had the luck that we had a special recruiter employed by the executive board of our university, and she worked in the end. She worked almost exclusively for my department because we were going this way. And that helps a lot. So those recruiters, they come up with their own candidates. They have their own networks. They came up with names that I would have never thought of, even though some of the profiles were in my field. So it does make a difference to have professionals in the organization to do this, and then divide the tasks between the authority, who does the approaching of the people, and the recruiter. Now I created a virtual vacancy. For that I put to life again the University of Harderwijk. Harderwijk is a small village in the Netherlands. The university actually existed twice. It existed in the period of 1848 until 1811, and then it was reopened again for 3 years, but then it was finally dissolved. But one of the buildings is still there. This is the Linnaeus Tower. Linnaeus studied there. So this is where I put my virtual vacancy, and this is the topic. Now we can distribute this little piece of text. First only the black. I'm getting over time. What you will see now is a unprocessed text of an advertisement I found on the internet for a vacancy. I will not tell you the location, but it was a vacancy in the Department of Marine Technology, something I think. That was the real place, but I will not tell you I changed the names of the cities. If you look carefully to the text, and then first form yourself an opinion. We will not have time to go over it completely, but I will give you 3 minutes to read through the text and see if you detect things that you think that are explicitly diversity unfriendly.
Who does not have the exam sheet right there? I think you can carry on.
Yeah, well, I will wait a few minutes. So after, let's say, how late should we end here, maximum?
Well, we are past the time.
Okay, so I will then wait for 2 minutes only.
You are free to use the pen.
Okay.
Okay, so we have the clearance from the
Yeah. Well, how long does it take to read this? 2 minutes or so? 2 or 3 minutes? The first question I will ask you is, do you think this is a bad text in terms of diversity enhancement? You must be reading a lot of text. And, when I was dean, I had to do that also. Every 2 weeks or 300 of pages I had to read in the weekend. Yeah, you learn to read very quickly. Well, you can also finish this a little later. Maybe first you must have gotten to halfway the text now. That is already good enough. Who of you thinks that this is a bad text in terms of diversity improvement? This is about 20% of the people. What I will do is I will demonstrate that it is actually a very bad text. And I will show you why this is. You will get the corrected version as well after we finish this. So this is the text. All the formulations which are non-diversity friendly have been made red. The first one, earliest possible appointment. Typically, female candidates are in big demands and they need more time. They may have children, so you have to accommodate time. So don't ask for earliest appointment. Give people time. Leave out the time constraint in total. This is one of the things to do. Then here are the descriptions of the research field. You see here this fairly detailed. This is a profile in marine biology or marine technology, but you see that it's tidal fluid dynamics, Bassin analysis, paleo, what words I cannot even pronounce. This is much too detailed. So with this, with statements like this, with like 5 or 6 constraining words that constrain the field, you eliminate many potential female candidates who just are a little bit outside this narrow field. So formulate much broader than this text. Here it's again a restriction. It says here that it should be the case that the research is relevant to the regional context. I put here the IJsselmeer because that's where Harderwijk is. The original text had another region. To a few of you I will disclose which university this was. This is again a restriction, which is not what you should do. So, and when you describe the content of the position, don't restrict too much. Be very open. Here, again, the teaching should be even more open than this. Here the teaching is already limited as well. So you have to be able to teach all this stuff. There are not that many people in the world who can give this cocktail of lectures. So don't do this. Don't restrict the pool that you are viewing. Again, here it is. These are standard texts that almost any university puts in. Your work has to be cited, so you need internationally peer-reviewed publications, successful acquisitions of funding, willingness to participate in committees of academic self-administration. These are things the people already know. You don't have to tell them this. They will not apply if they don't fulfill this. So don't put extra restrictions if they are not necessary in the text. If they apply to any position in any university, then there is not a reason to restrict yourself any further than that. So use the common knowledge, what is known, what is required for university positions, and not describe everything again, because this is interpreted as constricting. And here it should be, of course, a PhD is required, although this depends on the discipline. I know that, for instance, in our architecture department, a PhD is not required. And I know many professors who don't have a PhD in the architecture department. So it depends on the discipline whether you need it. But for physics or electrical engineering, it is a requirement, so then you can just put it in. But then don't put in outstanding. In some countries, the outstanding doesn't even exist. So then if you have graduated in a country where the outstanding level for a PhD doesn't exist, you might not apply here. So leave away these small requirements, unless you want to limit yourself to the countries that can facilitate this. Further academic achievements are expected. No, I don't know what they actually mean with this, so I would never put in that sentence. And then there is, well, this could be a matter of law also, when it is a requirement, like it is here. Yeah, for full professor habilitation. So if you're recruiting for a full professor, then if you then have the requirement of a habilitation, if I would apply here, I cannot, because in the Netherlands we don't have a habilitation. So what this means is that you cannot, if you want to do that, if you want to constrict yourself to the countries that do have a habilitation, fine, but know what you do with things like this. So all restrictions which are not necessary, leave them out. Then there are, this is actually the worst section of the whole document. The first sentence, open to all applications irrespective of gender. Why is that needed? Is there anything else which is gender or not gender? Or so this is a sentence which is totally useless. And it is again, what it also does, it sort of fakes attention for gender issues. It pretends attention for gender issues, but it doesn't actually do anything. So this is a sentence we should not use. This is a strange sentence which is completely counterproductive, I think. What it says here is applications from women are particularly welcome. Fine, that's so far yet. And will be treated with priority if they have the same qualifications, as long as there are no clear reasons which make a fellow applicant more suitable. So what it says, if we have a man we like better, we hire the man. So this is, well, this sentence, when I saw this, I thought, well, how bullshitty can you make it? This is really as counterproductive as you can do it. I would not apply, if I would have been a woman, I would not have applied because of that sentence. Yeah. And then the other one, the last one, application costs, so travel expenses, are not covered. If this is a law issue, there is no escape. If it is not a law issue, but a university rule, change the university rule, because this limits the options for people coming from poorer countries or people who are on a limited budget elsewhere to apply. So, what you see there, and then the final statement is also, this is at the end, it has the name of the location where people can file the application. There should be not the name of a recruiting person, there should not be corporate recruiting, there should be a name of a colleague who is recognized in the field, or an executive in the department, one of the two, so that people can actually contact a person and not a mailbox. So these are all issues which may seem very small, but these are the issues that determine whether you will be successful, whether you can be successful in hiring a diverse workforce. Thank you very much.